Hi, I'm Chem's best friend. I make chemistry easy. I'm a graduate of MIT, and I have more than 17 years of experience teaching AP chemistry and chemistry classes. Please like and subscribe to my channel. And if you are interested in private tutoring lessons, the information is on the screen. Hello, long time no see. Are you ready to learn about acids and bases? I am. Let's go. So let's look at this picture. Can you find which one of these products are acids and which are bases? Are you ready to play the game? Let's go. Baking soda, acid or base? Base. Toothpaste, acid or base? Base. Some kind of cleaning solution, Pro-Clean, acid or base? Base. Wow, maybe there's a pattern. Batteries, acid or base? Well, did you hear of battery acid? Acid. Lemon juice, acid. Coca-Cola, acid. And tomatoes, are they acidic or basic? Tomatoes are acidic. Wow, all the products on top are bases, and all the products on the bottom are acids. And let's see if we can find something in common. Well, all of these have something in common. They are cleaning products, right? You can use them to clean either kitchen countertop or your teeth, yes? Or put them in a wash, laundry. And these ones are all something we eat. They are acidic. So let's write some of these observations that we wrote. What are some properties of acids and what are some properties of bases? So where would we find acids? So acids are found in the kitchen. Where in the kitchen? I'm going to say acids are foods, right? The three things we saw pictures. We could eat them. Where are bases found? Where they are cleaning products. So they could be found in bathrooms, laundry room, or under kitchen sink. They are cleaning products. Did you ever taste acids? What do they taste like? Acids taste sour. Think of citrus fruit. Very sour. Now, bases, you probably didn't taste them, but maybe. Did you ever wash your hair and some shampoo happened to go in your mouth? They taste bitter. We really have an aversion to bitter taste as human beings, and there's a good reason for that. How do acids feel? Well, you will not really feel you have an acid on your hand unless it's a very strong acid and concentrated. You will otherwise, lemon juice, you will not feel it. It will not feel different than water unless you have a little cut on your skin. Or if your lips are very chapped and you are eating tomatoes or drinking lemonade, you will feel it. So I'm going to say they sting or burn if you have a cut on your skin. Otherwise, nothing really. Now, bases, you will know they feel slippery. Think of soap. Slippery, slimy. Soap is a base. While acids are corrosive to metals. Do you remember our single replacement reactions and activity series? Where we can put magnesium ribbon and hydrochloric acid, what happens? Magnesium ribbon disappears, right? So acids are very, very corrosive to metals. Bases, on the other hand, are very corrosive to, I'm going to say, living creatures. So we have a soap, it's a base, and it kills germs. So the concentration of soap on our hands is not enough to kill us based on our size, but it is enough to kill a germ based on germ size. So bases are corrosive to living tissues. When you wash your hands with soap, if you do it over and over, especially in winter, your hands get really dry. Soap is not doing good things to your skin cells. So this is why we have such an aversion, such a bitter, we don't do too bitter taste, because bases are not good for us. And acids, what else do acids? They will turn litmus paper red. That's one of the tests for acid. Here it is, red. And you're going to say red. Let's change this. Red. Acid ends with D, and red ends with D. Here it is. And bases will turn litmus paper blue. And here is the blue. And bases start with B, and blue starts with B. And last thing, for acids, they will have pH, will be less than 7 on pH scale. And that will be a topic on another video, the whole pH scale. And bases, pH will be more than 7. And 7 will be neutral, like pure water. Okay, so let's talk about a little bit more better definitions. So we have properties of acids and bases. Let's go to definitions of acids and bases. So the first person that came up with a very simple definition of an acid and base is this one, this Svante Arrhenius. Here he is, Arrhenius, and that's why we have Arrhenius' definition of acid and base. And he said that acids increase H plus ion concentration, bases increase hydroxide ion concentration. There it is. So we have our 6 strong acids. Some people say also, well, you see perchloric acid, HClO4. Some people will say chloric acid, HClO3. They were also listed. So some chemistry textbooks say 7 strong acids, some say 6. Just please keep that in mind. So some textbooks also list this one. But we have our 6, 7 strong acids. So we have perchloric, chloric, hydrochloric, yes, hydrobromic acid, hydroiodic, nitric, sulfuric. These guys really will increase H plus ion concentration. And here we have strong bases. Have a look at periodic table where they are. These ones, we have lithium hydroxide, sodium hydroxide, potassium hydroxide. They are your group 1 metals. Yes, group 1 metals with hydroxide. Here it is. And then we have calcium hydroxide, strontium hydroxide, barium hydroxide. These are our heavy group 2 metals. Yeah, our alkaline earth metals. Do you see them on the periodic table? So these are our strong bases. And strong bases will split apart into their cation and hydroxide ion. And strong acids will split apart into the H plus ion, yes, and their anion. So acids increase H plus, bases increase OH minus, hydroxide. And also here is a quick litmus paper. Also here is something that's acidic, turning it red. And here is basic. You can see basic is turning it very dark blue. Okay, are we ready? So then, why is ammonia a base? Let's have a look here. So ammonia is, we can see NH3, and let's draw a quick Lewis dot structure of ammonia. So we can see here is nitrogen with 3 oxygens. And notice ammonia doesn't have OH in it, right? It doesn't have OH in it. It doesn't have a hydroxide ion. So how can ammonia be a base? Well, let's draw water next to it. Here's water. And remember, there's a very strong attraction here between this lone pair of nitrogen and this hydrogen. Actually, it's so strong that it's hydrogen bonding, right? And sometimes if this water molecule gets a little bit closer, what will happen is Let's go to different color. What will happen is these electrons will actually attack this proton, and then these electrons will go back to the oxygen. So what we're going to have is, well, let's see, we have ammonium ion. We have ammonium ion made. This is here. And we're going to have what will be left over? Oh, our hydroxide ion. So what happened? Did ammonia increase the hydroxide ion concentration? Here it is. So ammonia did increase our hydroxide ion concentration. However, I think we need a better definition. Arrhenius' definition is too simple. We need a better definition of acids and bases, yes? So we do. We have now Bronsted-Lowry definition of an acid and base, and it's named after these two chemists. Bronsted and Lowry were their last names. Amazing. Okay, what did they say? They say acid is an H plus donor. So acid gives up an H plus. Base, what will base do? Is an H plus acceptor. Base will be ready to accept that. So with this definition in mind, let's go back to our ammonia example. What happened here? So ammonia accepted an H plus. Yes, so ammonia here is a base. Let's highlight this H. This is our special H. It's right here. What gave up an H plus? Water gave up that H. Water gave up an H. Ammonia accepted it. So based on our Bronsted-Lowry definition, water here is acting like an acid. Water is acting as an acid. Let's keep that in mind. Okay, with this example, let's do something else. Let's go here. What happens in this case? We put acetic acid, and here is our formula of acetic acid. Here's a picture and a formula, and we put it in water. What happens? Well, you can see after the arrow, we have acetate. We have our acetate and our hydronium, which is our H plus hydronium ion. What is going on? Can you figure it out? So here, let's look here. We have this hydrogen is next to the lone pair of an oxygen and water molecule. Do you see it? So this means right here, we have hydrogen bonding. If this water molecule goes a little bit too close, guess what? It might just say, hey, give me that H. Let's highlight this H that we are talking about. Here is this hydrogen, yes? It says, give me that H. So what will happen? So it will attack this H right here, and these electrons will go to the oxygen. So let's draw that. Oops, change the color. And right here, we will have our CH3. And here we will have C, double bonded O, O minus. Yes, our acetate plus. What are we going to have? Our hydronium ion, and it also should have a bracket, and this one should have a bracket too. Bracket with a negative charge. Here we go. Yes? So do you see it? So this hydrogen is right here. So let's go and think about our definition of acid and base. Remember, acid is an H plus donor. Base is an H plus acceptor. So let's go here. So acetic acid is, what is acetic acid doing? Is it giving up an H plus or accepting an H plus? It's giving up its H plus. So acetic acid is an acid. That's why it's named acetic acid. But the water is acting here as a base. So water can act as an acid and a base. Depends on an example. And in this case, we can now go into a definition of what's a conjugate acid and base. Now I want you to pay attention right here. So you have to imagine playing catch with a ball. right? So how do you play catch? One person is holding the ball, and one person is hands like this, ready to accept the ball. Yes. Let's look at the picture here. The ball is right here, H plus. The turquoise, that's our ball. Right here, the orange sphere is holding the ball. Whoever is holding the ball, that's an acid, right here. Green ball is ready to accept it. Whoever is ready to accept the H plus is a base. So now look what happens. This turquoise ball is going from orange to green. Now, green caught it. Who has the ball? Green. Green is an acid. We call it conjugate acid. So this is green without the H plus. Yes, that's a base. Once it catches H plus, it's a conjugate acid. And now our acid, once it's an acid, has the ball, has the H plus, it gives it up. Now it's only orange sphere by itself. That's a base. So we have a conjugate acid base pair. So right here, let's go to our example here. Acetic acid is an acid. Once it gives up this H plus, it's going to act as a conjugate base. And water here is a base. Once it catches the H plus, now it has the ball, it has that highlighted H, yes, that's a conjugate acid. Let's go to the previous example we did with ammonia. Do you remember? Let's go here. Okay, ammonia is a base, water is an acid, the H plus left water, ammonia coated. So let's go here. After ammonia accepted the H plus right here, now it has the ball, right? It has the highlighted H. What do we call it? It's conjugate acid. And water gave up. Yes, water was acting as an acid, gave up the ball, gave up an H plus, and now it's conjugate base. Did you get that? Would you like to do a few more examples? I think we should do another example. So one more time, let's have a look at this picture. We are playing catch. You're going to follow who has the H before the arrow, who has that H plus after the arrow. So let's go to these examples. Let's try this. So we have hydrofluoric acid reacting with water. So where is the H? Where is it going? Can you see it? So we had a compound, hydrofluoric acid, HF, and then it doesn't have a H. Now it's just F minus. So that means this must have been acid. And what happened to water? Water was H2O, and now it caught that H, yes, accepted the H plus, so water must have been acting as a base. So we have acid, give up its H plus, and now we have conjugate base. And when water was a base, accepted the H plus, and now we have conjugate acid. There we go. One more example. Are you ready? I think so. Let's look here. We have HCO3 minus. What is that? Well, do you remember CO3 2 minus is carbonate? So this is our hydrogen carbonate or bicarbonate. Yes. With water, let's look at the difference. Here it has one hydrogen, and here it has two hydrogens. It must have accepted an H plus. Wow, where did it get that H plus? Well, here water, H2O, and now you remove it H, OH minus. So hydrogen carbonate must have been a base here. Yes, base. And it accepted the H plus and it became conjugate acid. And this is now carbonic acid. And the water must have acted as an acid. Yes. And gave up its H plus. Now it's hydroxide. So we have our conjugate base. Is this making more sense? I want you to notice something really interesting about water, that in some cases it can act as a base, in some cases can act as an acid, depending on conditions. So here we go. This is just a summary. So water can act absolutely as an acid right here, where it gives up an H+. Here it gives up an H+ to the green ball. Or it can act as a base, where it accepts the H+ from the purple ball. When something can act as an acid or a base, the word for it is amphoteric. Amphoteric. Another substance that's also amphoteric is actually from biology, amino acids. They have an amino end, which can accept an H+, and then they have carboxylic acid end, which can give up an H+. So that's why we have amino acids. So anything that can act as an acid or a base, amphoteric. Okay? Let's go to just one more idea about acids and bases. And the thing is, what's a strong acid versus weak acid, and what's a strong base versus weak base? Well, weak bases, strong bases, same idea, strong acids, weak acid. Okay, so let's look at this picture. We have our hydrobromic acid and hydrofluoric acid, HBr. So let's look at the beaker with HBr, and what do you see? So the orange spheres are Br minus. So this is our Br minus right here. Oops. Wanted it to be, so this is Br minus, and the little spheres is H+. And this is F, and this is my H, hydrogens. And okay, so when you put hydrobromic acid in water, it 100% dissociates. You can see every H+ is separated from its anion. 100% dissociates. That's your strong acid. Now look at weak acid. And we can see that 9 molecules are together. The hydrogen and fluorine stay together. Yes, and then here we have 1. Here is our fluoride, F-, and here is H+ swimming. So so here's my F-, here is H+. Very few break apart. So that's the definition. So strong acid, 100% dissociates. Weak acid, around 1% dissociates. Around 1% breaks apart. So when we have a strong acid in water, we have HBr reacting with water, we draw one-way arrow. Because once it dissociates, it's not coming back. One-way arrow, it makes H3O+ or Br-. Now, H3O+, for many chemists, it's the same thing as H+. We just understand that H+ doesn't exist because this H+ will piggyback right on the water molecules. H+ is the same thing as H3O+. So just keep that in mind. That's interchangeable. And we can actually rewrite it like this, that HBr, hydrobromic acid, will just break apart into H+ and Br-. But in real life, the H+ quickly will grab a piggyback ride on a water molecule and it will become H3O+. But for weak acid, we write HF plus water, and we also actually write a double arrow. Yes, because once it dissociates, it actually will be coming back. So it doesn't really want to give up this H+. So we write this. So that's the definition of a strong acid and a weak acid. And the same thing applies to strong base and a weak base. Okay, so today, I hope you learned about properties of acids and bases, and you have a better idea of conjugate acids and bases. And I think we are ready to learn about pH scale and actually do some calculations with acids and bases with pH scale in the next video. So see you next time.